Okay, let's get started. So I didn't, let's see here. How is the homework going? How was Saturday's homework? It was great. Like to hear that? How about the one due tonight?
Oh, the one, yeah, the Saturday's one was pretty solid.
Okay.
This one was
Was that this one?
Yeah.
2? Triple integrals 2? All right, so let's look at 2. This one has the lowest success. We'll just talk about this one momentarily here. So we got evaluate the triple integral x dv, where e is a solid bounded by the paraboloid. X equals 7y squared plus z squared. Okay, so where's the vertex of that paraboloid? And which way does it open? And then is it circular or elliptical? Circular, opens in the positive x direction, right? Maybe something like this. Okay, and so maybe where I drew that circle can be maybe where I drew that circle, here's the x-axis, is the plane x equals 7. So maybe this is 7 right here. So how are we going to do this? So now it's not telling you which. I was in class, I was saying let's do this type, let's do this type, let's do this type. You get the choice. So choose the easiest one, right? Choose the one that makes the most sense. So first of all, is that going to be, do you think type A, type B, or type C? In other words, which dx first, and that was our type B. So dx first means. So what's our mantra here? Why is it? Why doesn't it? Why do you go? Where's my pen going away there? That's really weird. Something touching. I think there's like an ant on my trackpad or something. Let's try it over here. All right. So dx, and dx means what to what first, right? What to what? Back to front. So the archer is back here. The archer is shooting arrows from back forward in the positive x direction. And where do those arrows pierce into our solid? Is it one surface or more than one surface? Just one. And which one is that? Paraboloid. X equals. Yep. And then those arrows leave the solid in the front, right? So they're coming forward in the positive x direction. So this front, is the front all one surface or multiple surfaces? All one again. Okay, and what is that? X equals 7. All right, and then we have what? The outside double integral, which is this thing projected into which plane? They're saying YZ. Agree with that? Yep. If we're going back to front, and then we're going to project into the Y's, this whole solid into the YZ plane. How does that project into the YZ plane? Circle. So that projects as circle. Something like that. We'll project into the YZ plane as a circle. So we can draw that circle. And what is its radius? Yeah, so when x is 7, you're going to get the circle of radius 1. Forgot about that over there. It's like the no ink zone over here. All right, so circle radius 1. And so then we're going to go to just, type 1, bottom to top, left to right. So the bottom is, so this is basically the unit circle in the YZ plane, right? Centered at 0, 0, radius 1. So it's going to be square root of 1 minus y squared, or, 2. So we're going to bottom to top, right? So this is the circle y squared plus z squared equals 1. So the bottom is negative radical 1 minus y squared. The top is positive radical 1 minus y squared. And then we're going to go from, z goes from, or sorry, y goes from negative 1 to 1. So weird. I started making this other one, then I wrote up here on this one. So you have to. So I'm going to use those same limits, and this is what I want. And so, we never mentioned evaluating triple integral, but we evaluated lots of double integrals. Triple integrals is the same thing. You just have one more layer. So let's just do this. So maybe the difficulty has been in the actual evaluation. So let's do one here. So with respect to x, antiderivative is 1/x squared, and that's from 7y squared plus z squared to, okay, and then you're going to get what, 49 halves minus funness. Is that where the difficulty is? 7y squared plus 7z squared squared over 2. Did I do the math right? And I'm going to integrate that from what to what? Now I'm doing that with respect to y.
Easier to do polar.
Maybe possible to do polar. So this is seemingly impossible here. By standard, straightforward antiderivative techniques, I've got 7y squared plus 7z squared squared. I don't have a y out here. If I had a y out here, I would essentially have a chain rules derivative, right? Because of the derivative of the inside is y. I don't have that y.
Now we just have to distribute.
What's that?
We can do it.
Oh, it's just a, yeah, it's just a, yeah, that's not bad. We can FOIL it, right? FOIL and just do a polynomial. Sure, let's do that. We'll come back to it later. I promise we will. All right, so.
I don't want square roots.
So I want to talk about a new coordinate system. So far we've dealt with what's called the rectangular coordinate system. Why is it called that? Because everything's based on rectangles and rectangular prisms.
Really?
Well, not our, what about our pillars, right? Our pillars for Riemann sums, those weren't squares, right?
Oh,
So those were rectangular prisms, right? So a rectangular coordinate system, and sometimes we chose, dy to be different than dx, right? We chose a little change in y to be different than change in x. So we get a rectangle, not a square. So now we're going to talk about what's called cylindrical coordinates. But we've almost kind of already done this, okay? So once you see what this is about, you're going to say, oh, this is like, we've already really kind of done this. So cylindrical coordinates are based on the three coordinates are r, theta, and z. Where r and theta are our standard trig. These are our standard trig or polar coordinates. And z is the same z as before. So what does that look like? That looks like we're going to sweep an angle theta. We're going to sweep an angle theta. Standard trig angle. Everyone see that? Same one as before. Counterclockwise from the x-axis, our standard theta. So we're going to sweep an angle. Then we're going to choose a radius at that angle. Although we put r first, just like polar coordinates is backwards, right? You want to think about theta being independent and r being dependent, or yeah. But they put it first. They put r first. But theta really comes first. Pick a theta, then you pick an r. So distance from the pole, or distance from the z-axis, and then you pick a z. And with those three coordinates, you can get any point in three-dimensional space, just like you could with x, y, and z. So what is this? This is the point. What did I just graph? I just graphed the point 3.25. This point right here. It's 3.25. 2.23 for radians. And 6.15. So that is that point in polar coordinates. What would it be in rectangular coordinates? So this is my r, theta, and z. Same point in space as x, y, and z would be what? How would we get the x-coordinate from these cylindrical coordinates? Alexander knows. We should all know. How do we get the... Nicholas, is that a hand? Can you tell me? How would you get the x-coordinate if we knew that r was 3.25, theta was 2.23, and z was 6.15? Z would be, no, but I just want the x-coordinate. But yes, z would be the same. That's true.
X would be half the radius.
Half the radius.
No, it would. X would be.
So how would we get the x-coordinate? Yeah. Michael,
It would just
sorry.
be x equals r cosine theta and y equals r sine.
Right, so just like we found x and y coordinates and polar coordinates, be r, so 3.25, so let's actually plot that point. So Shreyas, is that what you're going to say?
Yeah.
So tell me what the x-coordinate is for this particular one.
The 3.25 times cos 2.23.
Okay.
Y would be 3.25 times sine 2.23.
And what would be my z-coordinate?
Which is
Still 6.15. Let's see if that... So you get a point in the same place? Make it bigger. Yep. So that I just graphed the x, y, z coordinates of the point, and I'm showing you that it landed in the same place as r, theta, z of 3.25, 2.23, and 6.15. Make sense? I'll write this again. 2 pi over 4, 1. 4. 1 pi 3. 3, 7 pi over 4, negative 1. So plot those points in R3. And then sketch these, whatever this set of points turns out to be. And then sketch R equals 4. Z equals 2. And theta equals 5 pi over 6. So the set of all points that have the R coordinate of 4. The set of all points that are Z equals 2. The set of all points that are theta equals 5 pi over 6. Sketch those. Oh, and in cylindrical coordinates, we only have to worry about r being greater than or equal to 0. So we don't really deal with negative r, like the way we did in polar coordinates. We can allow for negative r values. In cylindrical coordinates, we pretty much stick to r being greater than or equal to 0. Okay. So just getting a hang of the coordinate system, so I want you to plot these points as given as cylindrical coordinates, and then I want you to sketch whatever this turns out to be. These are three different exercises. R equals 4 is its own exercise. Z equals 2. Theta equals 5 pi over 6. Those are separate exercises. Sketch whatever that set of points is for each of those. Okay? Work together. If you need help, ask. Right? Making progress or getting help.
Z equals 2 just a plane.
Yeah.
That's a vector. And then the theta is equal to what?
5 pi over 6.
So, are there any of the points that you want me to plot? Any of those that were challenging, slightly challenging? Want me to go over? Good on the points? I'm happy to go over one. Okay. So, what about r equals 4?
It's gonna be 2.
What's that?
It's gonna be a 2. The previous one.
No.
Oh,
It's thinking a different r there, so we need to trick it. So how can I, instead of putting r equals 4 in here, what can I put into GC here, my software, to actually show the r that we want, the r equals 4 that we want? What should I put in? He's suggesting x squared plus y squared equals 16. Is that going to be the r equals 4 that we want? Some people are nodding. Let's try it. Why? Because that's, what kind of thing is that? It's not a circle. Cylinder with r equals 4. That's why they call it cylindrical coordinates, because a constant value of r gives you a cylinder. You see? Constant value of r gives you a cylinder. So it's based on cylinders, right? Based on moving up and so different z value. Yeah. So a constant r is a cylinder, and then at different z values we basically have circles, right? What was next? So that's r equals 4. Theta equals 5 pi over 6. What's that?
That's just like a ray going out in the 5 by 6 direction, and then let Z get equals.
Okay, that's a ray if x squared plus y squared equals 16 is a circle. Not a ray. Oh, wait, maybe you weren't done.
Wait, what?
So what is theta equals 5 pi over 6? Is it a ray or is it something else? Daniel.
I don't know what it's called, but it's like a vertical plane.
Okay.
It starts at the z-axis, it goes infinitely in 5 pi over 6 direction, but it doesn't come back through.
Okay, what were we going to say, Ellie? Same thing?
And
Yeah, so we call it like that. We call it a half plane. Half plane. So it's right. It starts at the z-axis and only goes in the direction of 5 pi over 6. Now, there's nothing characteristic about this plane that it should stop in the circle, right? It's just, it'll keep going infinitely up and down and out at 5, 5, or 6. So for some reason it's cutting it off. It's only so it's here. It's only showing up to 7 away from the origin. So if I made this, like 100, all you'll see is, there we go. Right? So there's only that one moment when it's facing you. There you go. Boom, gone. The back is good. So you're seeing that it. Yeah. Okay, next. What was the last one? What will that be? What kind of plane? Horizontal plane. Horizontal plane at 2, right? That's the same as equals 2 we've always had. Okay, so what is this? Cylindrical coordinates is basically just a polar plane at any z level, right? And so you use the polar coordinates r and theta at any z, get you all points in space. And you have the same conversions that you do between polar and Cartesian coordinates that you had before. So we'll do a triple integral, and so cylindrical coordinates then would be integrating over a function of r, theta, and z. And if you start with a function of x, y, and z, you have to transfer it accordingly, right? What is x? X is r cos theta, y is r sine theta, z is z. Okay? And then we're always going to, in cylindrical coordinates, we'll always go bottom to top first. And then what after that? R dr d theta, right? And so we'll go bottom to top, and then this will be our polar double integral. So we've kind of already done it, right? We've kind of already done these triple integrals whenever we did a what? Whenever we did a type A, and then our outside double integral, we did it in polar, then that you were essentially doing cylindrical coordinates when you were, if you ever did something like that.
How many types does this one come with?
This is it, just one. I mean, the standard cylindrical coordinates are where you have r and theta in the xy plane, and then z. But you can have cylindrical coordinates in terms of x. Ever seen that before? So lots of you were getting mad. Let's just do polar. Let's just do polar. Let's just do polar. You're right. Yes. Good madness. Good madness. Okay. So let's do it. A lot easier. So now, so basically, now we can just do cylindrical coordinates with what? Our first variable now being x instead of z. So it's going to be, so use coordinates like this, r theta x. But then this r and theta is in the yz plane. Yep, so y would be r cosine theta, and z would be r sine theta. And then rather than z being the last coordinate, x is the last coordinate. Okay, and so then we have, now we can do it fast. Yeah, so we started evaluating the triple integral, and we proved that in cases like this, cylindrical coordinates, much, much, much better. So 7y squared plus 7z squared is 7r squared. 7. And then the outside double integral is going to be the disk, which will be theta goes from 0 to 2 pi, r goes from 0 to 1. Or usually we do r dr d theta. So you totally can do r first. Doesn't matter, but usually, or so you can totally do theta first, but usually do r first. And then what will we integrate? X is going to be? X is still x, right? Because that's our That is a coordinate, right? We know it's not our cosine theta because now in this cylindrical coordinates, it's like based on cylinders along the x-axis. X is x coordinate. And we'll have dx, r, dr, d theta. But just make sure you know your dr, d theta is in the yz plane now. Yes, sir?
Does it actually matter which y and z we assign r sine theta and r cosine theta? If we decided that we wanted z to be r sine theta and y to be r cosine,
That would mess it up because of how we define the angle theta. So theta is counterclockwise this way. That's our theta going around like this. And based on that theta, horizontal coordinate is cosine, vertical coordinate is sine. So if you do that, then you're going to get sign errors, SIGN errors, because of the way that the angle is defined as counterclockwise from the horizontal axis. So yeah, you want to make sure y is our cosine theta and z is our sine theta. Other questions? So, right? Okay, so now let's do a triple integral on cylindrical coordinates. And since it's kind of stuff we've seen before, I kind of have a more challenging one, which is good because we've seen lots of triple integrals. So let's work on a harder one. See if we can get it done by the end of class. We got 12 minutes. Set up the triple integral cylindrical coordinates to integrate. We just want to set up the integral. I want to integrate f r theta z over this solid. Okay, outside of x squared plus y squared plus z squared equals 1. Inside of x squared plus y squared equals 9. Below x squared plus y squared plus 3. And above z equals 0. And confined to negative x less than or equal to y less than or equal to x. This is fun. This is a nice geometry challenge. So we're going to try, let's do our best. Can you make a sketch good enough to render this thing? It doesn't have to be perfect. It doesn't have to be a perfect image. But when you make these images, they have to be good enough for you to solve the problem. So can you make an image good enough to solve this problem? Try not to spin your wheels at the beginning. Get off to a good start. Work together, okay? And I can help you.
I just think it's not that way.
Like that one.
How about y is less than x? How would you sketch that? What is y is less than x? What points is y less than x?
Below the y equals x curve.
Right, exactly. Below what? Y equals x. Because it's all y coordinates less than when y equals x. So then we also have, so that's this, right? So imagine everything below that.
And then it's everything above the y equals negative x curve.
So where would that be?
In that region you drew there.
So here's y equals negative x, and we want everything what? Yeah, but there's 4 places that are between those two.
Hey, he's adding on to this. This is where the balance.
So which is it? Y is less than x and greater than negative x. Top left, bottom or right? This, right?
Yeah.
So what is that for theta?
That's negative pi fourths to pi fourths.
Yeah, this is really specifying theta. This is really specifying the values of theta. So it's theta from negative pi over 4 to pi over 4. That's what that does. That condition gives you this. And so you see how I've drawn that there, then? From negative pi over 4 to pi over 4? Okay, where does the arch, so now we're going to set up the limits. Where does the arch, questions on what I drew? Do you follow? That kind of was, maybe your drawing wasn't perfect. Mine isn't either. But as long as it's good enough for you to imagine it correctly. All right, so questions on the solid we're integrating over, right? What's going on there? There we go. Okay, smooth that out. All right. So, where does the archer fire from?
From like
Where does the archer fire from? In which direction?
from under it.
From underneath shooting up. DZ is our first, right? It's going to be DZ, DR, D theta. Fires up from the bottom. So, pierces into the bottom of this thing. One surface or multiple surfaces? Multiple surfaces, okay? So, let's, according to what? What are the possible surfaces? Sphere and z equals 0. And so those are basically, you got this, that's the sphere, right? And then the plane z equals 0 will be a sector out here like this, right? Better. A little bit darker. It's too. Oh no, it's too blue to match the sphere, right? Sky blue. That's what I wanted. So where that's that you have that sector, that's the sky blue sector, that's coming through that, and then I think I have gray. The orange is like the gray plane. Make sense? What's the rate? So what is this radius right here? Right there? Is that 1? And this one is 3. So we're going to have r from 0 to 1 is going to indicate one triple integral, and then r from 1 to 3 is going to give us the other triple integral. When z starts at what? So we're going to have true. If you need to go, you can slip out quietly and watch the video. If you want to stay and watch it, we can stay and watch it. But if you need to, this will all be on the video. Okay, so z goes from, in one case it goes 0, and in the other case it goes from the sphere. So the sphere is x squared plus y squared plus z squared equals 1. So what will our lower bound be then? Square root of 1 minus x squared minus y squared. But what's that? R squared, right? So it's going to be z equals square root of 1 minus r squared. Because that'll be 1 minus x squared minus y squared. And then now, so that's where the arrow pierces in. It pierces in at 0. Or it pierces in at 1 minus r squared. Where does it pierce in at 0? When r goes from? Right. When z equals 0 corresponds to r going from 1 to 3. So that's why I write it over here where z is. Okay, so yeah, so when the arrow pierces in at z equals 0, that corresponds to r being from 1 to 3. And when the arrow pierces in through the sphere, that's r from what to what? 0 to 1. Does that show up for the sphere? Good enough. Here, very easy fix. Except it messes up our thing. All right. Okay. Next. Where does z end? Where does z come out? One or more surfaces. One surface. What surface is that? The paraboloid, right? Z equals what? R squared plus 3? So in both cases, we exit out the paraboloid, r squared plus 3. That's this part right here. For the entire radius from 0 out to 3. Okay, and finally, theta goes from negative pi force to pi force, and that's for both of these, right? It's the same. So then we're just integrating f, and then we know our dv has the r in it, right? It'd be dz r dr d theta. All right, I'll leave it up if you want to ask.